Okay, so I'm going to present some work I did for my master's project with my project partner, Julia, that you saw earlier, and our supervisor, Yaseman Yazdi. And the question we were trying to answer was, can one hear the shape of a quantum spacetime? Okay, so quantum gravity, in part, is a difficult problem because it seeks to unify fields that have different mathematical bases. So QFT uses the language of mathematical analysis, whereas GR is based on differential geometry. And these frameworks are very different. And a field of mathematics that can bridge this gap is spectral geometry, because it can give us an analytical way of talking about geometry. So spectral geometry is essentially the field of mathematics that answers the question, can one hear the shape of a drum? So if you only have the sound the drum produces, are you able, from that information alone, to reproduce its shape? And more mathematically, that means studying manifolds through the eigenvalues of canonical differential operators on them. And this is what we call the spectrum. And spectral geometry is very well understood by mathematicians on Riemannian manifolds. But because we're interested in spacetimes, we want to study Laurentian manifolds, and very little work has been done on that front. And the reason we're interested in this is because it could be useful for quantum gravity. So, for example, if one has to sum over quantum spacetimes, it's not obvious how to add up geometries, whereas converting to spectra and then summing over the spectra and then converting back to spacetimes is much more intuitive. And so this is why we ask the question, can one hear the shape of a quantum spacetime? So to make the problem slightly easier, we worked in the framework of causal set theory. So causal set theory is a theory of quantum gravity in which spacetime is fundamentally discrete. So the continuous spacetime manifold emerges from an underlying discrete causal set, a causal set being a set of elements with a partial order. And so the elements, each element is one spacetime event, and the partial order gives us the causal relations between these events. So here's an example of a causal set. So causal sets are usually often represented by their Hasse diagram. And so in this case, we have a 5-element causal set where each node represents a spacetime event, and the arrows show you which event causally precedes which other events. So for instance, event 1 precedes event 2, but also precedes event 5 by transitivity. But event 5 and 4 are not causally related at all, and so we cannot say if one precedes the other. So, and the reason causal set theory simplifies the spectral geometry problem is because operators on causal sets are, because causal sets are finite, operators I mean, you can use, because causal sets are discrete, and when you study finite causal sets, well, the operators are discrete finite matrices with the finite spectrum. And so this is much easier to study than differential operators on Laurentian manifolds, especially numerically. And so the question now is, what kind of operators can we study? So one of the most obvious operators is what we call the causal matrix, which is defined by this relation here, which is if at position x, y in the matrix, if element x causally precedes element y, then you have a 1, otherwise you have a 0. And so this completely specifies the causal set. The issue is the causal matrix is not suitable for spectral geometry because it has a trivial spectrum. And so instead, we have to take combinations of the causal matrix, such as its self-adjoint parts and its anti-self-adjoint parts. Okay, so if we want to study specific spacetimes, so specific dimensions or curvature, we have to have a way of generating causal sets that corresponds to these spacetimes, i.e., causal sets that can embed into these spacetimes. And to do this, we use a process called Poisson sprinkling. So the idea is that you have your manifold, and then you pick points in that manifold to put for your causal sets, and then you endow the causal relations by using the metric of the manifold. So that's how you find the causal relations. And the idea is to have to sprinkle the points such that you have a probability of having endpoints in volume V at density rho, given by this formula, which is just a Poisson distribution. And so here we have an example of a 100-element causal set sprinkled into a 1 plus 1D causal diamond. One detail is that not all causal sets can be embedded into manifolds. So there are so-called non-manifold-like causal sets. So an example here is what we call a Kerr order, which has 3 slices of time, and this cannot be embedded in a manifold. And one important problem in causal sets is how to identify these non-manifold-like causal sets because they're not physical. And so in our project, we wanted to see if using spectra, we could distinguish equivalence classes of causal sets. For example, causal sets of certain dimensions or non-manifold-like causal sets. Okay, yeah. So here is a plot of the spectra of different causal sets. So flat causal sets sprinkled into flat spacetimes of different dimensions from 2D to 7D, as well as a Kerr order. And so here we've plotted the eigenvalues of the self-adjoint part of the causal matrix, and we've plotted them in order of magnitude. And this is in a log-log plot. So as you can see, we have the same behavior for the spectra, and we have first a straight line and then a breakdown. So the breakdown can be explained by the fact the causal sets are finite, so this is expected. And the straight lines, because we're in a log-log plot, are power laws. So the spectra seem to obey power laws. Interestingly, the Kerr order, which is the only non-manifold-like causal set in this example, has the flattest spectra. So this could be exploited to identify it. If we fit the power laws, if we fit the power law part of the spectra, we can get the powers. And what we find is that the power obey a monotonic relation with the dimensions. So you can order the dimension by looking at the powers alone. So 2D has the largest power up to 7D with the lowest. And interestingly, again, what I was saying about the Kerr set having the flattest spectra can also be seen here, where the power is very different from all the other ones. So this gives us hope that we can use the spectrum to completely determine the dimension of a causal set. Finally, there is another way of studying the spectra of spacetime, and that's asking the question, instead of just looking at the spectrum as is asking the question, how does the spectrum behave when the spacetime changes? And so in causal sets, this is done by using co-perturbations, which is essentially adding elements and links to a causal set. So here we have the causal set we showed before, and we've just added a co-perturbation in red. And so the question is, how does the spectrum changes when we do such a perturbation? And the way we can quantify this is by using the spectral distance, which is the sum of the differences of the eigenvalues of the original causal set and the co-perturbed causal set. And so what we have done is we have done this for many different causal sets, and we've in this case we've perturbed every element of the causal set and then calculated the spectral distance between that completely perturbed causal set and the original causal set. And we've done this for different curved and flat spacetimes and different dimensions, and also non-manifold-like causal sets. And the interesting part here is that, again, the non-manifold-like causal sets seem to be separate from the other one. So here, again, we have a log-log plot. So we have straight lines, which indicate power laws. And the two non-manifold-like causal sets, so here KR1 and KR5. So I showed the KR set previously. KR5 is just a similar non-manifold-like causal set, but with extra layers in the middle. And we can see that both of them are outliers. And so again, we seem to have a signature for non-manifold-like causal sets in the spectrum. So to conclude, can one hear the shape of a quantum spacetime? Well, we have found evidence that one can in fact hear the dimension of a spacetime as well as its manifold-like nature. Thank you.
Thank you very much, Antoine. Do we have any questions? There's one coming in the chat. I don't know if you can see it.
Okay, do you think it could provide an experimental signature or rule out the extra dimension of string theory and theory? So I'm not too sure about that, but what is something that has potential is that, so I haven't talked about it here, but this work has some connection with something called the spectral dimension. And instead of talking about extra dimensions, what this gives evidence for is the dimensional reduction at small scales. So in some theories of quantum of discrete spacetimes, you have dimensional reduction at very small scales, and so this could show up in the spectrum. So there is possibility for that. I don't know about extra dimensions. I mean, yeah, no, I don't.
There's a second question come in.
How does one get the spectrum information to then infer information about the Causal set? Is it from some sort of observable? There's no, I mean, I don't have any idea of how this could have any, how you could find a spectrum experimentally. But what we have done is purely like numerical. You look at certain operators and you find the eigenvalues and you plot the spectrum, I guess. There is, I mean, yeah, in the sense of observables, what might be observable is, for example, if we find some connection, if we find a concrete connection between dimension and the spectrum, well, then seeing the dimension might give you indications about the spectrum, but the spectrum itself, I don't think is observable.
Can I ask a question before we wrap up? So earlier on, you said that the spectrum for the causal graph, or what's it called, the matrix was trivial, so you take this symmetrized version.
Oh, yes.
Does that correspond to sets that are time reversible then?
Okay, so there is that as well. So here, the reason we did this was simply because the original matrices can be put in upper triangular form, so you just need another matrix, but it does have a connection with this. So when you do this, it does give you the causal matrix of a time reversible causal sets. And I talked about the spectral dimension briefly before, and it has connections to this as well. So yes, I guess is the answer.
So what does that mean in terms of the emergent space-time?
I mean, we haven't thought about that, I guess. We haven't assigned a meaning to the spectrum and the operators, I guess. We've just seen if the spectrum has some patterns in them, if that makes sense.
And for the anti-self-adjoint part, I can't remember if you actually showed a result for that.
No, I haven't. So so you have some similar patterns in the anti-self-adjoint part, and you can also take the commutators of both. In each, you have some similar patterns. I think the self-adjoint part has the cleanest example, and it also has some connections with that spectral dimension that I mentioned before. So that's why we chose that one.
Okay. Well, it's fascinating. Thank you for the talk.
Thank you.
I think we're at the end of the session there. So thank you again to all of our speakers, and apologies again for Antoine for missing him out the first time round.